Hi everyone, today I will be presenting our project Crystal LLM, the designing of the materials by autoregressive large language models. At a high level, our goal is to use artificial intelligence to generate entire new crystal structures that satisfy the real-world physical constraints. Metal discovery is traditionally a very slow process. Researchers often spend years while designing, simulating, and experimenting and validating the new metals for a battery semiconductors, catalyst, and new energy applications. The central question was asked, can we use the modern generative AI to accelerate material discovery? The large language model such as GPTs has shown incredible capabilities in generating text, code, and images. However, crystals are fundamentally different from language. A crystal is governed by the symmetry, atomic interactions, thermodynamical stability, and geometric constraints. Unlike text generations where a slightly incorrect sentence may be still understandable, a small error in the crystal structures can make the metal physically impossible. Therefore, our challenges was not simply generating the crystal files. Our challenge was generating the crystal files that obeys the laws of physics. This provides explore how the LLM models can be combined with a graph neural networks and physically guided such algorithms to achieve the goal. So, our core challenge. Before discussing our solution, it is important to understand why crystal generation is difficult. Let's examine the three major challenges. Challenge number one, symmetric constraints. Crystals belong to a specific space groups. A space group defines a symmetric operations such as rotations, reflections, and translations. Every atom placed inside a crystal must respect these symmetric rules. If the generated structure was violates even one symmetric operation, the crystal becomes invalid. Unlike the natural language, there is no tolerance for approximations. Challenge number two, thermodynamic instability. A second challenge is stability. Even if a crystal looks correct geometrically, it may not exist in reality. Materials scientists often use the formation energy to determine whether a structure is stable or not. Negative formation energy indicates stability. Positive formation energy indicates instability. Therefore, our model cannot simply generate the plausible structures. It must generate the energetically favorable structures. And our challenge number three is continuous coordinates. Crystal structures are using stored by the CIF files. CIF files contain highly precisable decimal coordinates. For example, 0.1254, 0.3457. These numbers represent exact same positions. Traditional NLP tokenizers we never designed for this type of information. They often break the decimals into subwords and the lose precision. Therefore, standard language modeling approaches struggle to preserve the spatial information. These three challenges motivate the design of our system architecture. To address these challenges, we designed a modular microservice architecture. The architecture consists of the four major layers. Front layer, the first layer is the React and Tailwind front end. This is where the users interact with the systems. The researchers specifically constraints such as chemical compositions, phase groups, formation energy target, and number of formula units, and the gateway layer. The second layer is a Node.js gateway. This layer manages authentication, routing, API management, database, and interactions. So MongoDB Atlas stores user sessions and generated results. AI interface layer. The third layer contains the heart of the system. A Python fast API service hosts 124 million parameter language model. Allen graph neural network. This layer performs the crystal generation and evaluation. Physical simulation layer. The final layer performs computationally intensive simulations and validation. One important design decision was separating the AI models from the web application. Initially, all the components exist in a single backend. Heavy simulation caused timeouts and performance degradation. By isolating the AI interface into dedicated microservices, we improved the scalability and stability and maintainability. The architecture design was critical as the model complexity increased. Demo pipeline. These slides demonstrated the workflow followed during the generation. The process begins with a user-friendly constraint. For example, generate a gold oxide Au2O3. The target formation energy negative 2 electron volts per atom. Specific space group Z value equal to 4. These constraints are passed to the language model. The model generates a candidate crystal structure in a CIF format. The CIF file is processed using a ASC. ASC stands for Atomic Simulation Environment. ASC converts the generated structure into a format suitable for visualization and analysis. Finally, NGL views renders the crystal in an interactive 3D environment. Researchers can rotate, zoom, and inspect the atomic arrangements. This allows the immediate verification of structure quality and physical possibility. The entire pipeline transforms user consciousness into visualized crystal structures in real time. Byte level tokenization. Our one of the most important contribution is solving that we can call spatial blindness. Let's understand the issue. Traditional language models use byte pair encoding or BP. BP merges frequently occurring character sequence into larger tokenizer. This works extremely well for natural language. However, for CI files are not natural language, they are structured scientific data. Consider a coordinate 0.123. A tokenizer might split this into the multiple tokens. As a result, spatial information becomes fragmented. The model must spend valuable training time to relearning the syntax instead of learning the material science. To solve this problem, we implement a byte level tokenizer. Every character is treated independently. Numbers, decimals, white spaces, and the symbols are preserved exactly. This creates a one-to-one mapping between the original file and the tokenized representation. Benefits include better coordinate preservation, faster syntax learning, improved spatial accuracy, reduced training inefficiency. As a result, we achieved a raw syntactical validity rate of 56%. The insight might here is sometimes performance improvements come from the better data representation rather than the larger language models. MCTS plus Align Physical Supervisor. These slides represent the core intelligence of our system. Even a very perfect formatted CIF file may describe an impossible material. Therefore, syntax alone is insufficient. We need physical awareness. Our solutions combines two perform align techniques. First one is align. The first component is uh, it stands for Atomistic Line Graph Neural Network. It models crystal structures as graphs. Atoms become nodes, bonds become edges. Using graph representation, Align can predicts the material properties such as formation energy and the Monte Carlo tree search. The second component in Monte Carlo tree search. MCTS is commonly used in decision-making systems such as AlphaGo. Instead of generating a crystal into a single path, MCTS explores multiple paths while generating the paths. At every generation step, the language model proposes candidate atoms and coordinates. Align evaluates each partial structure. MCTS alliances rewards based on the predicted stability. Stability branches receive higher rewards. Unstable branches receive penalties. Poor branches are discarded. Promising branches continue to expand. This generation creates a feedback loop between the generation and the physical evaluation. The language model acts as creative generator. Align acts as physical expert. MCTS acts as decision-making engine. Together, they ensure the generation is guided toward physically realistic materials. This is a major improvement over unconstrained generation approaches. Uh, Engineering challenges. Every research project encounters obstacles. Crystal LLM was no exception. The challenge number one, Windows compatibility issues. The DGL framework and Align introduced multiple DLL dependency conflicts. Several backend libraries were not fully compatible with our environment. After extensive debugging, we stabilized the system using the compatible library packages and a PyTorch LTS release. And challenge number two, autoencoder limitations. Initially, we explored autoencoders. However, autoencoders struggle with the discrete atomic counts and the structural constraints. The generated output often lack consistency. We therefore pivoted to the autoaggressive transformers. The transformers naturally model sequences and discrete tokens. The architectural challenge significantly improved the generation quality. And our challenge number three is backend bottlenecks. Running the LLM and GNN together caused memory pressure and latency issues. Request frequently timeout. Our microservice refactor solved this problem. Separating interface services improved reliability and reduced the cascading failures. These engineering lessons were important as the scientific contributor themselves. Let's examine the results. Our system uses 124 million parameter autoaggressive language model. Through byte level in tokenization, we achieved a 56% syntactically validity. This means more than half of the generated structure satisfies CF formatting requirements. Additionally, our physics grounded framework targets thermodynamical stability to the formation energy optimization. For demonstrating purpose, we use a target formation energy of negative 2 electron per volts for golden oxide. Where there is still room for improvement, these results demonstrate that combining the large language models with physics guidance is a viable strategy for inverse material design. To conclude the crystal LLM demonstration, that material generation requires more than simply scaling languaging models. We introducing three major contributions. First, byte level tokenization preserves partial precision in the crystal coordinates. Second, MCTS combined with the LN provides physically guided generation. Third, user controlled parameters allow researchers to directly influence generated structures. Together, these innovations bridge the gap between the probabilistic AI generation and the deterministic physical laws. Looking ahead, the future work could include the larger models foundations, better formation energy predictors, experimenting, validating in laboratories, multi-objective optimization, discovery of noble battery and the semiconductor materials. Ultimately, our vision is to create the great AI systems that assist scientists in discovering the new materials faster than ever before. Thank you for listening. I would be happy to answer for any questions. Thank you.